So in our history lesson, we left off with the Bohr model of the atom. Yes, it was Chadwick who discovered the existence of the neutron, but that wasn't as major or significant change in the structure as Bohr's idea that Rutherford's atom wouldn't work. The electrons that are zipping around in circles are going through accelerated motion, and when charged particles accelerate, they radiate energy, which means they should all lose their energy and spiral in and collapse, and Bohr fixed that by just saying, of course, electrons do not lose energy. Now, it wasn't quite a mic drop moment like that. He didn't just say that. He said they don't lose energy when they're in orbits of specific radii. Okay, he didn't just say that either. Right? He actually had some reasoning to back it up. He said electrons do not lose energy when they're in orbits of specific radii because when they occupy those orbits, their angular momentum is quantized. Because that makes much more sense. Okay, let's talk about this. What was he doing? Well, okay, so Bohr was studying the motion of electrons. He was studying their angular momentum. All right, so let's remind ourselves of the equation for angular momentum. We actually had two different equations, but we're talking about electrons. Electrons are really tiny, so we can consider them to be point particles. Let's see if you remember what's the equation for angular momentum for a point particle. Right, L equals R P sine theta, or R cross P. Okay, so remember R is the position vector, and it just happens to always be at right angles to the momentum vector because we assume they're going in circular orbits, so the angle here is 90 degrees, sine 90 is 1, and I'm just going to replace P with mv, so in this case it equals R times mv, and sine 90 goes to 1. Okay, so here's what Bohr figured out. By studying the angular momentum of these electrons, he found out they were quantized, which means they came in chunks, in stepwise, sort of a stepwise function. And it turns out it was always some multiple of h over 2 pi. So here's h again. Here's Planck's constant just showing up somewhere completely different, right? And so the angular momentum, R equals mv, is some integer times h over 2 pi. So n is just 1, 2, 3, 4. Came in these multiples, these discrete chunks of h over 2 pi. That's what it means to be quantized. Now all I'm going to do is I'm going to mess around with the algebra here. I'm going to flip-flop the 2 pi and the mv. So on the left-hand side is 2 pi r. The right-hand side is n times h over mv. Check the algebra. I'm sure you see that, of course. Haven't done anything wrong here. This is kind of interesting because 2 pi r, what's that? Oh, that's circumference. Wait a second. H over mv, what's that? That's de Broglie wavelength, isn't it? So he found out that the circumference of these circular orbits here is some integer number of wavelengths. Now this looks a little familiar. Maybe it doesn't. Let me rewrite this a little bit, because circumference is the length around a circle. So I'm going to call this L for length. Now I know it's already confusing because this is the L for angular momentum, this is L for length. These are completely different L's, but I write it like this because now it looks a little bit familiar. Why don't you just pause the video and see if you can figure out what condition this is, where we've seen something just like this before. Did you figure it out? Where an integer number of wavelengths have to fit on a certain length. This is the condition for standing waves, for resonance, isn't it, right? Let's remind ourselves. Let's say we have a slinky or a string or something that's stretched out some length L. And let's say if n equals 4, that means that we got 1, 2, 3, 4 cycles, 4 wavelengths can fit on there. Or if it were n equals 3 or n equals 2 or n equals 5, whatever it is, that's got to be an integer number of wavelengths that can fit on there. It can't be a fraction of one, right? Then it's not going to work. It just won't fit. Okay, so this can help us visualize standing waves, but these electrons aren't going in straight lines, they're going in circles. So I want you to imagine the straight line here, the equilibrium line. We're going to sort of bend it like so, bend it around like this, and then I want to fit these same 4 wavelengths on it. So let's split this into 4 equal parts. I'm trying to do 1, 2, 3, 4 equal parts. And then we're going to draw cycles in each of these sections, right? So here's 1 cycle, 2 cycles, 3 cycles, 4 cycles. Please pardon my crude drawing skills here, trying to freehand it. This still is not quite right because the electron has to go in a circle. So imagine taking the equilibrium line and bending it all the way around into a circle, where again we want to fit those 4 wavelengths in there, so we can split it into quadrants, and each wavelength is going to fit in one of these. So here's 1 cycle, 2 cycles, 3 cycles, 4 cycles, and I'm going to get rid of those dividing lines so we can see a little more easily. So this is basically a circular standing wave. Why is this significant? Well, the whole point is, let's say if we just start here, the wave goes 1, 2, 3, and then by 4 cycles, or an integer number of cycles, it sort of feeds back in on itself, which means that there will be no loss of energy. That's what Bohr is saying, that electrons will not lose energy when their circular orbit is of a certain radius, a certain in this case a certain circumference, so that the electron wavelength given by the de Broglie wavelength has an integer number of them, so the energy feeds back in on itself. This is genius. This is crazy. Okay, now I may be having some trouble visualizing exactly what we're showing here, so let me switch over. Here's an animation of a circular standing wave. So this is the n equals 4. At any given time, you see 1, 2, 3, 4 cycles. This is the picture you just drew in your notes, but now you're seeing it sort of oscillate back and forth, and that's what we're trying to visualize here. With this animation, I can change it. Maybe it's n equals 5. Now, for that same circumference, 5 wavelengths fit around. Or maybe it's n equals 3. Here we have 3 cycles fitting around. That's what an n equals 3 circular standing wave looks like. Here's n equals 2. Right? At any given time, there's 2 crests and 2 troughs. Pretty cool, right? Here's n equals 1. Kind of boring. Just 1 crest and 1 trough, but there it is. Let's go back to n equals 4. So here's what we're trying to visualize. Now, this is not really a great animation, because what should really be happening, if we're trying to see this as being representative of the electron orbit, is that every single time I go from 1 to 2 to 3, if I increase this, the radius should increase as well. That's not what this animation is made to do. This is really just for the circular standing wave so you can visualize it, but if we really want to be technical about it, for n equals 1, this would be a relatively small circle. N equals 2 is going to be a larger circle. N equals 3 is a large circle, because it needs to fit more and more cycles. The circles have to get larger and larger. You will fit maybe 4 cycles in this case. Okay, now just to be clear though, we're not saying by drawing this picture or watching the animation that the electron actually goes through this wave-like path. The dashed line is the path of the electron. The electron goes in a circle. Okay, electron goes in a circle. Because an electron is a piece of matter, it has a wavelength. That's what de Broglie said, right? And its wavelength is given by h over mv. What Bohr is saying is that if an integer number of these wavelengths, h over mv, an integer number, 1, 2, 3, 4, can fit in that circle, then the energy gets fed back in, and the electron won't lose energy, and that solves the whole problem of the whole atom collapsing in on itself. But I want to be very clear. I know it's very difficult to visualize what's going on here, because this is incredibly abstract, and it's very, very weird. But the electron goes in a circle. But the electron is an object in motion, so it has a wavelength. And if that circle is of such a circumference, such a length around, that an integer number of its matter wavelengths, its de Broglie wavelengths, can fit in that circle, that's a stable orbit. However, if the circle were a slightly different size, one way or the other, then we can't have an integer number of wavelengths. The energy would not get fed back in, and it wouldn't work. And so that's why it's only orbits of specific radii that match an integer number of wavelengths. That's the idea. That's really what we're trying to say here. Now, the other kind of crazy thing about this is that Bohr came up with this idea in 1913. De Broglie didn't postulate that matter could have a wavelength until 1923. So Bohr figured this out and had some conceptualization of this before the idea of matter waves even existed. And so then when de Broglie came up with the idea, he was probably reading what Bohr had done. He sort of fitted together. This was really strong evidence that Bohr's model works.